class, welcome to EdVantage. I'm Dr. Sujatha Krishnaswamy, your chemistry professor. Today we're going to take a look at two very related topics, matter and energy. So what is matter? Matter is defined as any substance that has mass and occupies space. So what is mass? Mass is not weight. Those are interchangeable terms in chemistry. However, they are different. Mass is the amount of matter contained in any object, whereas weight is the gravitational attraction of the earth towards an object. So to a physicist, they're very different terms, but to a chemist, they are often interchangeable. We can divide matter into any one of the three physical states: solids, liquids, or gases. So what this means is how they appear to us when we look at matter. They could appear as a solid, liquid, or gas. So what is it that makes these three very distinct states of matter? There are three properties that define whether you're looking at matter as a solid, you're viewing it as a liquid, or a gas. The first one is shape. So if a solid has a very rigid shape, it doesn't change its shape. Of course, you could take a hammer and beat a solid and it'll change its shape, but otherwise it's just going to be the shape it has all the time. A liquid will take the shape of the container. So if you take a can of Coke and move it to a glass and then move it to another container of a different shape, it's going to take the shape of the container. And gas will also take the shape of the container. When you take a look at the properties such as volume, a solid has a fixed volume. Its volume doesn't change. And again, a liquid's volume doesn't change even if you change it from one container to another. Whereas a gas will change its volume. You could take the gas in the entire room and you could compress it into a tiny cylinder or even an ampule. So it does have very variable volume. The third property that defines these states of matter is compressibility. It's very hard to compress a solid. Similarly, a liquid is hard to compress. You can compress it a little bit more than a solid, but still negligible when you compare it to a gas. You can take an entire room of gas, and as I said earlier, you could compress it in a little ampule. Now, why is it that you have such varying properties for solids, liquids, and gases? So let's take a look at the molecular picture, or what is really happening within these three states of matter. So in a gas, we have those red particles. That's what makes up the matter. And you can see there's a lot of space between those particles. So what this means is there's enough room for these particles to move. And that's why they have variable shape and variable volume, because they can move between the spaces between the particles. In a liquid, you have some space. You can change it from one container to another. That little space between the particles does allow it to take the shape of the container. But in sharp contrast is a solid, where you have absolutely no space between the particles. They are really attached to each other, and therefore it has a very rigid shape, very fixed volume, and has no compressibility. You just don't have any space between the particles to bring them close to each other. Okay, now we're going to take a look at the three states of matter and see if they are interchangeable. In other words, can they move from one state of matter to another? So if you take a solid and you apply heat to it, it can melt and become a liquid. If you apply more energy to it in the form of heat, it can become a gas. If you take away the energy from a gas, it'll become a liquid. You take away more energy, it's going to become a solid. These transformations have very specific names. Solid to liquid is known as melting. Liquid to gas is known as evaporation or vaporization. Gas to liquid is condensation, and liquid to solid is freezing. These are terms that you might have encountered in your daily life. There are a couple of the terms that you may not be so familiar with, and one of them is converting a solid directly to a gas by skipping the liquid state, and that is called sublimation. A common example of sublimation are mothballs that you would throw in a closet, and it's nice that the solid mothballs become a gas. And because of the pungent odor, they kill the insects. You obviously don't want puddles of liquid in your closet. So that's a great example for sublimation. Another example is camphor. If you burn camphor, it just gives you that strong incense and it becomes a gas. It skips the liquid state. The reverse, taking a gas into a solid, is called deposition. And this has great applications in semiconductor industry. So if you want to coat a silicon wafer, you really take it to a vaporized state, and then you will deposit that particular vapor directly on a silicon wafer, and that is a solid once it's deposited, and this is called deposition. So it has great value in semiconductor industries. So we're going to classify matter into two types. So we just talked about classifying matter into solids, liquids, and gases, and that's based on appearance. Now we're going to classify matter based on what it is made up of. So again, we have two classifications here. These are mixtures and pure substances. Two examples there on the screen. One is a pizza, the other is sugar. So if you take a close look at it, the pizza has many different ingredients in it, so I would call it a mixture, whereas the sugar has only one type of substance in it, and that is sugar. So that is a pure substance. So here is one matter which is a mixture, which is a mix of many substances, and then the other kind of matter is a pure substance, which is made up of only one type of substance. There's another major difference between mixtures and pure substances. Mixtures can be separated into their components, which means you could take the pizza, as clumsy as the process may be, you could actually pick out all the olives, the tomatoes, and you could get all the ingredients that you store it with. So it's possible to physically separate a mixture. With the sugar, you can pick all those crystals out, but you really don't, it's all sugar, it's made up of only sugar. So you cannot physically separate it. So I don't want to make a very important statement here. You can chemically separate it, which means you can take the sugar, take it to your chemistry laboratory, and you can perform reactions, and you might be able to separate it into something, but physically using a pair of tweezers or looking under a microscope, you wouldn't be able to remove anything from the sugar. It'll all be sugar crystals. And that's another major difference between mixtures and pure substances. When we take mixtures, we can further divide them into two kinds: homogeneous mixtures and heterogeneous mixtures. So homogeneous mixtures have uniform composition throughout. So if I take a glass of water and add a spoon of salt to it, just a common table salt, and stir it really well, and I want you to sample the top portion of the glass, the middle portion of the glass, and the bottom portion of the glass. Sampling could be something very rough, like you tasting it, or you could even send it through a very expensive analysis. You'll find that the composition is the same throughout, and that is called a homogeneous mixture. A heterogeneous mixture does not have uniform properties. So if I take another glass of water and add a spoon of sand to it, stir it the best you can, and then I want you to sample different portions of that glass, water and sand in that, you're going to find that certain portions are going to contain more sand. Hopefully the bottom portion will contain more sand, because sand is denser. It will quickly settle to the bottom. And you're going to find a varying composition throughout this sample, and therefore it's called a heterogeneous mixture. When we take the pure substances, we can further classify them into two kinds. We would call them compounds or elements. So compounds are made up of at least two different elements. A very common example is water, and it's made up of two elements, hydrogen and oxygen. So you can separate a compound into elements, whereas an element cannot be broken down any further. So what that means is an element is the simplest form of matter. So an element is not made up of any other type of substance. It would be the simplest form of matter. For example, gold is made up of only gold. You must clearly see the difference between compounds and mixtures. So compound is not a mixture. So mixture is made up of two different compounds, whereas compound is made up of two different elements. Now let's talk a little bit more about elements. There are more than 100 elements known. 81 of those are stable. Some of them are not stable. So what does it mean? You can take some of the elements, put them in a bottle, come back after 10 years, and they are exactly the same. Some of them you put it in a bottle, come back after 10 minutes, they are not the same. They're constantly degrading, giving out energy, converting themselves into something else, and therefore those elements are unstable elements. Here's a nice diagram which compares the distribution of elements on Earth's crust and human body. In both cases, you can see oxygen is the major component, major element found in both the Earth's crust as well as the human body. Another interesting fact to see is in the Earth's crust, silicon, which is part of sand, is the next major element, whereas in the human body, carbon is the next major element. As we progress further with our lectures, we can see the relationship between carbon and silicon and how these two diagrams will make a lot more sense as we go forward. Every element has a name, and the name is very unique, which means no two elements will have the same name. Names have different origins. Sometimes it could be from a language, sometimes it is from a country where it was discovered, sometimes it's named after a scientist and whatnot. So this particular website, Web Elements, will give you a lot about history of every element. If you're interested, you can go in and check that out. An element is also given a symbol. So instead of you writing the entire name of the element, you can write a symbol. The symbol is 1 or 2 letters long. Some elements have 1 letter and some have 2. For example, carbon's symbol is C, cadmium's symbol is CD. When you have 2 letters, the first one is capitalized, the second one is a lowercase. So here are some examples of elements and their symbols. Let me just go over a few of these. Aluminum is Al, where the first 2 letters are the symbol. Antimony has SB. You neither find S or B in the name antimony. So if you're wondering why it got the symbol SB, it's from the Latin name for stibium. So you do have some strange ones like that. As we go further down the second column from the bottom, second one, which is iron, the symbol is Fe. You neither see F nor E in the name, and that comes from ferrum. So you do have a lot of Latin and Greek names for these elements, and the symbols arise from those languages and not from English. So this gives you a few more examples of the elements. For example, tungsten is W, it comes from wolfram, and so on. Sodium is from natrium. So you do have a lot of Latin names. Now we take the elements, we can divide them into 3 categories. They are metals, non-metals, and semi-metals. Semi-metals are also referred to as metalloids. There are properties that will define that an element is a metal, and there are again properties that define it to be a non-metal. So we're going to look at what those properties are. Here's a kind of an interesting picture where you see in the first picture you see a bromine. That is an element, and it's a liquid, and when you pour it out of the bottle it's a liquid, but you can see right on top of the beaker it is becoming a vapor. So it's a very low boiling liquid, it's very volatile. And the next picture you see is mercury. It's the only liquid metal, and so that's kind of special about mercury. And the third one you see is a metal called gallium. It is a solid, but when you place it on the palm of your hand, just your body temperature is enough to melt that particular metal. So metals have very interesting properties. To just digress a little bit, the first element, bromine, we don't want to handle it. It's not a green chemical, because when you pour it out of the bottle you get these thick fumes, and it's a very heavy element. It can settle in your lungs and cause respiratory problems. So it's kind of important to know the properties of each element. And mercury, of course, is a proven carcinogen, and its use in thermometers have been banned for a long time, and it's replaced by alcohol thermometers. Gallium has very interesting properties because it does liquefy immediately. You cannot store gallium in a glass bottle because it'll expand. When the solid becomes a liquid, it'll expand and it'll break the bottle. So the point I'm trying to make here is every element has certain unique properties, and it's kind of important as a chemist to know that for its own safety and storage. So here are the properties of metals and non-metals. So metals are typically solids, non-metals are kind of soft solids or gases. Metals have a nice shiny luster to them, non-metals are typically dull. Metals are malleable and ductile, which means you can beat them into sheets. Think of the aluminum foil in your kitchen. You can draw them into wires like copper wires. Non-metals are very brittle, and for this reason non-metals are not used as conductors. They're not good conductors of heat and electricity. You can draw them into wires. That's why our metals are commonly used for conducting heat and electricity. Density is how much material you can pack in a given space, and with metals being solids, you can pack a lot of those particles in a given space. So it is very dense, whereas non-metals don't have very good very high density, it's very loose packing. Melting point is defined as a temperature at which the solid becomes a liquid, and metals have a very high melting point, and that is why metals are used as utensils. So if you put them on your kitchen stove, you don't want it to melt. You want it to last long and definitely not ever melt. So metals have great applications that way. Non-metals have very low melting points. When it comes to chemical reactivity, what do they react with? Metals react with non-metals, and non-metals can react with themselves, but also react with metals. Thank you for watching. I hope to see you again in the next lecture. We'll look at properties of matter.